Hello and good morning, afternoon or evening, whatever you are. So let's continue with our tutorial where we're computing the forces directly in Paraview. As I mentioned, there is no need to do that in Paraview, and the solver will give you that information. Right? But in any case, previous case was a steady case, quite easy. Now let's move to on a steady case, the classical cylinder. Okay, so we have unsteady data, and look at that here, our integrals and everything, and it's moving, comparing now my viscous forces, total forces, and so on. So I want to show you this. Pretty much to compute the forces are exactly the same as the previous tutorials. Probably the new addition here will be how to post-process this data, okay, how to get the data from the solver, plot the tables, and so on. So here we have, as usual, let me stop the simulation. You will find in the data, okay, the state to reproduce that. Here you have the inside data. Okay, I save the data from the simulation in site format, as I mentioned, is one light, but you can use whatever you want. And the data in this case is coming from OpenFOAM, but it doesn't matter the software. We have seen already that. And something interesting also that the data, for those who knows how to use OpenFOAM, when you get the forces, now you get this data like this. So I already pre-processed this data, and I eliminated these parentheses that can give you some problems on reading now the input file in Paraview. Let's say any software, even Nuplot, you will need to eliminate this. So it's just pre-processing now to erase those. Now to get this CSV, now the comma separated value or tab separated value. So after that pre-processing is a TSV file, now just spaces. So let's see how to do that. So I will start from scratch and using Paraview 6, but it should work with any older version. I don't know how old, but I guess at least 5.13 will work. So the first thing is that we need to load the inside database, dataset, or whatever format you chose to save it. So I will go here. So you have all the data. So as I mentioned, you already have pressure, wall shear, stresses, and from this data you can compute your total forces. So no need to do all that integral and so on. So basically what we're interested here is to get the forces in the surface, and the moments will be the same as in the previous video. So probably I will prepare another video for that, but no needs. We're interested mainly in the forces, okay? So basically let's do some. Now prepare the view here. So I want to have an slicer. I put it there. So this is my plane. You can put your velocity and so on. So now also let me go here, and I would like to work with cell-centered data. At least I will stay with the forces and use the cell-centered data. For the moment probably will be, it is easier to use the point-based data, but in any case. Now that I have this, let me go and extract selection. So it's the cylinder. Okay, so you have the cylinder there. And then we do now the traditional steps. So compute normal. So here I know that I need an extract surface there. Then I will need filters, alphabetical, then surface normals, which probably is easier to look. So there are many. So surface normals, and there you go. So you have your surface normals. Okay, the area, I'm not going to compute it. No, I'm not interested as I integrate, but you know that if you want to plot the forces on the surface, you should multiply by the area, but I'm not going to do that. So at this point, pretty much we're done. Let me add here the calculator, and let me call it TF for total force. And it will be, as you recall, is cell-centered data. It will P times your normals. Okay, I forgot here normals to get it in the cells. Okay, so always always remember to set that, or depending if you're doing cell center or point center. So I prefer to work cell center, but it's up to you. Nothing change. P normals and minus. Remember, this is important design. No, in OpenFOAM is minus. If fluent, it will be a plus. No, it will be the wall shear stress that is already a vector, and this will be your total force. And now you go here, alphabetical, and you are going to integrate this time series, okay? So if I play here, you see that it is changing the information now. So actually, let me stop here. So I want to see the cell center data and show me only the information I just computed. That was this one, TF, total force, that's all. Okay, so as you press play, you have there the forces changing. Okay, probably will be interesting. Yeah, let me show you also. No, I don't need to show you anything else. I was thinking about showing wall shear stresses, but I already have everything there. So you have that there. Now I want to plot this time series, not to see the animation. So this is important. You have another filter here, this one, extract selection over time and then plot. So I will select this. This is the data that I would like to plot over time. Click here. Yes, and before clicking yes, a warning, because this can be a very, very expensive operation. So in this case, it's a small data set because it's going to compute that in every time step. But if you have a large data set, be careful, okay? So apply, and then see that it will take some time. Something important, you need to select the data set here. When you apply that filter, you need to have the selection here. If you don't have a selection here, it's not going to compute anything. So just to repeat, you go here, select, click here, big warning before doing that, and here you should have the selection, okay? And see here that you have everything there, and click here, and let me go. I only want to see here TF, I think I call it. Now let me go, where do I have that? Okay, so I have the three components of that, okay, and I am only interested, let's say, for the first one, that will be X component, and there you go. So this will be your total drag force, okay? And now something also interesting that I want to point out, look at that, what you can resolve here in Paraview. Okay, what you compute is what the frequency that you get, the safe frequency that you get from the solver. So you will need a large amount of data to get that. Okay, so I don't recall, but I think it was like 1 second my saving frequency here, which is not enough to capture everything. So if you want to get precise frequency, you need a really low safe frequency, a lot of data, a boatload of data. Instead here, when you get this table, you get all that information. Yes, you don't get the colors, but at the end of the day, you are just interested in the quantitative value. Okay, so important to mention that. And now let's load this table. So you go here, open, load data, and I'm going to load this one. Okay, so important that I change the extension. So if sometimes on software they put point dat, change that. Is you put point that, is going to open another format here. It will be, I think, tech plot. So put point CSV, TSV, now comma separated value, tab separated value, and it will use the right filter. And this is it. So just to mention, the original data is this one. As I mentioned, I erased all the parentheses. Also modify a little bit the header, and I just put one line, and then I separate everything. A tag for each column that is important. So when this filter reads, will have the name, and also be careful that at the end you shouldn't have an empty line. So the original data set, I think, so it's not that it's going to crash, but it's going to add another column. So see that you have an empty line, so just erase that line. Okay, just prepare now, just tidying your data. Okay, so we have this one, and now here you have different options. So have header, so we have a header, we prepare the header. My field delimiter is not a comma, it is a space, okay? At tab field delimiters, there is a tab. How I don't know how it's defined in this filter, but it can be 4 spaces, 5 spaces, 10 spaces, whatever. So it might not be the precise one that you want to use here. So let me go back here and see that you have different tabs on the spaces. So here you have this tab, which probably is 10 spaces, I don't know, and then here you have 1 space. So the clever way is just merge consecutive delimiter. So you have here, you added your delimiter that is in a space here, then there is a tab, you apply, and you see that it will read it. Okay, so let me close here, put it here in the bottom. This is in a spreadsheet, and you have it here. So see that you're reading the header. Okay, you have your time, and no problem. So now that you have this, you can imagine that you only need to plot it. So to plot this, okay, you set it. Okay, let me go, and let me record this is the, let me go back here. So okay, so I have a calculator. Okay, so okay, yes, to compute the total force you can access the column, so you can apply also the filter calculator on your tables and input data. So I want to compute something, I will call it result. I will leave that name, and I want pressure X plus or minus, I think, yeah, viscous. Okay, so let me check. Yeah, this is always be careful how. Okay, it's plus. I already have it. Yeah. Okay. Yeah, you already have the in the table. You have the right. So apply. You compute that quantity, and then I can come here. So that, and there you go. You have that data available. Okay, and let me choose result. I want to visualize only result, and there you go. So you can see the difference where I was talking about. So the orange line will be the continuous, the tabular data. So see that it's not perfectly matched the peaks because you have different saving frequencies for the data. Okay, and you have everything there. Okay, so this is how it works. So this is your total force, so very good match, but be careful, your saving frequency needs to be very high. So small cases not a problem, you can put it there, but large cases that can be very expensive. So that is one of the reasons why not to do it in Paraview. But then if you want to plot the forces and the surfaces for distribution for whatever other post-processing, there is no problem. Okay, so be aware of that. So let's do now, for instance, so if you want to do moment, recall that moment, how we compute it is pretty much the same, but let's look at now at lift component. Okay, so pretty much we can go here, the calculator, I don't recall. Okay, we have everything, and okay, will be the second column here. So select that plot, and it will be this one. Okay, and let me go. No, I think it's not the correct one. Okay, I have it there. I have result. Okay, let me hide. Okay, I have result, that is the previous one. So let me hide this one. So see that we have there the lift component, which is 0 in average, but it is oscillating, pretty much what we mentioned. But anyway, something cool. You press play, look at that, you have this green bar there that is moving with your time, and you have your cool, nice animation. Okay, so you can do very cool things here in Paraview. Your integral changing in time, your bar here moving, and then you can plot on top the result coming from OpenFOAM, and then also you can compute all the statistics. Okay, mean, standard deviation, skewness, kurtosis, whatever you want. So you can compute it on this. Again, it's better to compute those average or your descriptive statistic directly in OpenFOAM, that you can have a very high saving frequency as you have these tables. Now, here to get a good average, you need to save a truckload of data, a lot of data to get a reliable statistic. So in any case, so now let's plot here this one, and I want to plot the lift. So again, here just come to the calculator and change now to Fy, which should be the lift force. And then if you want to compute the coefficients, another calculator, and use your reference values. And there you go. Orange line is the tabular data coming from this, okay, these files, TSV file, and the blue one will be the data, not the integrated computing in OpenFOAM. As you see, we have a good match there. Okay, so to show you also the importance of adding the two components, so let me get here, multiply the total force and the wall shear stresses by 0, and let's see what we get now. So even for lift, you will have this contribution of wall shear stress, and we'll see a small difference. So it's important now always to compute all these components. As I mentioned, there are some cases that wall shear stresses contribution is very small, so it's something now that you are not going to see, but most of the cases can be something that is not that you cannot neglect, okay, that you need to take into account. And see here the difference now we remove that component. Clearly we can see, okay, pressure force is the largest component, okay, but then wall shear stresses have another contribution that when you are not taking that into account, you don't get a perfect or a very good match. But at the end of the day, it is up to you. So yeah, there you go. This is how you compute unsteady data. Nothing changed, exactly the same workflow as before. If you want to go for moments, will be exactly the same. The only difference that now be careful that when you use this filter, plot the selection over time, this operation sometimes can be very, very time consuming depending on the data set. I recall that I have done this stuff usually for multi-phase flows. Now I want to do some operations and I have data set of 5 million cells now, simulation of 5 million cells, and this can take 10-20 minutes, okay? So be careful about that. But besides that, you work exactly the same. So yeah, this is cool. So a nice advanced feature, okay? Hopefully now we're going to work more in Paraview to show you more features. Now we receive a lot of requests. Probably this is the request that we will receive more often. How do I compute pressure, viscous forces? You have it here. Moments also, how to do this plot. So you have everything here. Then you can do your movie. Probably next video I can show how to do that movie. But yeah, it's straightforward. So yeah, that's all. Thumbs up if you like it. If you didn't like it, remember I only take positive feedback. No, just kidding. Just drop your comments in the section below, and well, hopefully see you next time. Enjoy and have a nice day. Bye.